this set of notes, we're going to look at the expected value of a function of random variables. So we're just going to start out here with the definition of the expected value. And so notice here we're going to define k different random variables, and we're just denoting them as y1 through yk. And then we're going to define some function of those k random variables. And so notice here we're going to have both the discrete and the continuous case. In both cases, we're looking at the expected value of a function of those random variables. And so you'll notice, comparing the two, the first thing we're going to do is, for the discrete, we're going to sum, and for the continuous, we're going to integrate. And so that's just like what we saw when we looked at the univariate case. And then further, notice what we're doing in each of these cases. Here, we're going to sum over the sample space for each of the random variables. And in the continuous case, we're going to integrate over the sample space. So again, very similar to what we did in the univariate case, we're just now doing this to account for the fact that we have multiple random variables. And then what we're going to do is, in the discrete case, we're going to sum over that function multiplied by the PMF. And in the continuous case, we're going to multiply the function by the PDF. And so again, very similar to what we did in the univariate case, we're just extending it out to multivariate. So let's look at an example. So suppose here we have two random variables. They're going to be x and y, and here we have their joint density. And what we're going to do is we're going to find the expected value of x times y. So starting out here, we're just going to start out with what the definition tells us. Well, x times y is a function of those two random variables. These are continuous random variables, so we're going to use integration. So notice that both x and y are restricted between 0 and 1. So I know I'm going to integrate over both of their sample spaces. The function I'm interested in is x times y. And then I'm going to multiply that by the density. I'm going to integrate with respect to x first and then with respect to y. You could flip those and you would get the same answer. So now we're going to solve this. First thing I'm going to do is I'm going to multiply through that x times y. Next, I'm going to integrate with respect to x. Here we're substituting in the x equals 1 and the x equals 0, and if we do that and we do the subtraction, you would find the following. And then again, if we integrate with respect to y, and since I'm running out of space, I'm going to skip that step, but do confirm on your own that you find 59 divided by 144. So again, very similar to when we found the expected value in the univariate case when we looked at a function of a single random variable. It's just now we have a function of two random variables, so we're going to integrate over each of their sample spaces. And just to confirm, try this integration where you first integrate with respect to y and then integrate with respect to x, and again, you should get the exact same solution. So let's look at another example here. Now notice this one is a little bit different than what we've seen before, because notice when we look here, we see that y is restricted between 0 and 1, but then also that x plus y is restricted between 0 and 1. So we've got two different conditions here. Notice that this suggests the following, that x plus y is less than or equal to 1, and that y is less than or equal to 1 minus x. So the first thing I'm going to do is I'm going to draw what that support space looks like. So I'm going to have x along this axis, y along this axis. Again, restricted between 0 and 1. We've seen something similar before. And notice here, because of this restriction right here, we know that this is our area that we are interested in, or our support space. So there's two different ways that we could solve this problem. We could use a double integral like we did on the previous problem, and that's what I'm going to do here in just a moment. Or the other thing we could do is we could refer back to our previous note set, and we could find the marginal distribution of x. And then, once we have the marginal distribution of x, we could find the expected value just like we've done previously in previous note sets for the univariate case. So again, I'm going to do the solution where we actually do the double integral, but I suggest, do find the marginal and see if the expected value of the marginal gives you the exact same thing. So again, we want the expected value of x. Now notice the reason I say that we could alternatively look at that marginal is because the expected value we're interested in is just a function of x and not of x and y. So again, we're going to look at the double integral here. I'm going to integrate with respect to x first, and notice that x is restricted between 0 and 1 minus y. And I'm going to integrate with respect to y second, and so in that case y is going to be restricted between 0 and 1. I'm interested in the expected value of x, and then I'm going to multiply that by my density. Again, you could flip these and integrate with respect to y first and then with respect to x. If you do that, the bounds on your integration are going to change. So integrating first with respect to x, we get the following. And then next we're going to integrate with respect to y. Oh, sorry, I just realized I wrote that step twice. I didn't mean to do that. Erase that. So again, doing that integration. And we find the expected value of x is equal to 1/3. So again, this is looking at that joint distribution. We're using the double integral. Alternatively, you could use the marginal of x. And just to help you check that you do get the exact same expected value, go ahead and check that. Find the marginal distribution of x. You'll need to do that first, and I'm going to go ahead and tell you what that is equal to, just so you know that you get the right solution. And then use this marginal distribution, and you should find that the expected value of x is again equal to 1/3. All right, we've got one more example here. So notice here the expected value we're interested in is a function of x. So let's see what happens with this one. So again, we're interested in the expected value of a function. We're going to use a double integral to integrate over that PDF. Okay. Notice here that we've got some cancellation, so I'm just going to rewrite this integral. Okay. So now first integrating with respect to x, we have the following. Which then yields the following. Then integrating with respect to y. And notice that this is going to give us the following. And so notice we end up with this term right here, which is undefined. So in this case, the expected value of that function of x that we were interested in does not exist. And so it is possible to have expected values that do not exist. So just be aware that that can occur, and if it does, it can happen. Double check your work, but that is something that does happen. There are several useful expected value theorems. Now, these theorems are going to look very similar to what we looked at in the univariate case. So for example, the expected value of a constant is just equal to a constant. If we have the expected value of a function of x and y, and we multiply that function by a constant c, then we know that we can pull that constant outside of the expected value. And then here in the last one, notice if we have the expected value of a sum of functions of x and y, then that is equal to the sum of the expected value of those functions. And so again, we saw something very similar in the univariate case. And then also similar, we have a result related to the idea of independence. So if x and y are independent and we have two functions where g of x is solely a function of x and h of y is solely a function of y, then we know the expected value of the product of those two functions is equal to the expected value or the product of the two expected values. So again, very similar to what we saw in the univariate case. All right, so the next thing we're going to talk about, which is related to the idea of expected values, is covariance. And so if you'll remember when we looked in the univariate case, we started out by, we talked about the expected value and then we moved into variance. Well, in the univariate case, you talk about variance. In the bivariate or multivariate case, we not only talk about variance of the individual random variables, but we also talk about the covariance. And so the idea is if x and y are two dependent variables, how dependent are they? And you can measure the dependence by calculating their covariance and their coefficient of linear correlation. So suppose that we take a random sample. Here we've got, you can think of this as being samples from two separate populations, the x 1 through n and then the y 1 through n, and then we could plot our data. So we're going to look at some potential plots that we could potentially see. And before we do that, over here in this square, I kind of want to think about what x and y could potentially look like in terms of their means. So here along the x-axis, we could have our x's and we could have our y's. And then we'll just arbitrarily start this somewhere, let's say 0, for example. Well, if we're thinking of this as the possible range that x could take and the possible range that y could take, we know that the mean of x is somewhere, here in the middle, and we know that the mean of y is somewhere here in the middle. And so we can think of this as taking 4 different grids where what we're interested in is going to be x minus mu of x and y minus mu y. And if we think of that product, we'll notice that the product is either going to be positive or negative depending on which of these four regions we're in. And so we'll use that here when we look at three graphs down below and we talk about the possible graphs that we could see. All right, so again, along here I'm going to put x, and along here I'm going to put y. I know that mu of y is somewhere in here, and mu of x is somewhere in here. And again, I've put 0 there arbitrarily. It might end up that the mean is negative. In that case, we could just extend that 0 down to negative infinity if we wanted to, but this is just for illustration. So one potential graph that we could see when we plot the x's and the y's would be something like this. Okay? In this case, we would say that x and y are dependent, and we would say the following. As x increases, y also increases. In other words, what we're saying here is if we look at the expected value of x minus mu x times y minus mu y, we know that that is going to be greater than 0. And again, this deals with this idea of this square that we have up here of what region we're in. And one thing to notice that this expected value that we're looking at, it looks kind of similar to when we talked about variance. Because remember when we talked about variance, one of the expected values that we looked at was x minus mu x squared. Well, but now we've got an x and a y, so instead of considering it by itself and squaring it, we've got the product of the two. Now the other thing that we could see, if we draw the same plot, is instead of going up and to the right, it could go down and to the right. We would still say that they're dependent in this case, but now what we're saying is as x increases, y is now decreasing. So in other words, if we look at that expected value of x minus mu x times y minus mu y, that is now going to be negative. And so what we're getting at here is really this idea of covariance. We see two different ways that x and y could be dependent on one another, and we see that that expected value is either positive or negative depending on that dependent relationship. Now, of course, the last option here would be that there is no dependency, or that they are independent. And so if they're independent, we're likely to see something that's just a straight line, a horizontal line going across. So, or in other words, we could say there's no clear pattern. And by clear pattern, what we mean is either the up and to the right or the down and to the right pattern. And so in this case, that expected value that we've been looking at will be equal to 0. That should be a capital Y there. Really, all of these should be capital Y, since y is a random variable. Let's change that. So that's the idea of what we mean by dependency. So here is our official value of covariance, and you're going to see our definition of covariance, and you'll see in that definition we have that expected value that we just looked at. So what is the covariance of yy? In other words, what would the covariance be of a random variable with itself? So we can apply that definition. And notice, this is what we will have. And that is the variance of y. So the covariance of a random variable with itself is just equal to the variance. And so there's lots of useful covariance facts. Just like when we looked at the variance, we could rewrite the variance as the expected value of x squared times the, if we took the whole expected value of x, that entire thing squared. So in other words, what I'm saying here is that the variance of x is equal to the expected value of x squared minus the expected value of x, that quantity squared. Notice we have a similar result in terms of covariance. It ends up that if x and y are independent, then the covariance of x is equal to 0. And if that covariance is greater than 0, as x increases, y increases, and if it's negative, as x increases, y decreases. And so these two facts are exactly what we just saw on the previous page. Now often we would like to standardize the covariance to make it unitless, and so we'll often look at the coefficient of correlation. And so one thing to notice here is that is not a p. That is the Greek letter rho. It often looks like a p. And so notice that the rho is equal to the covariance of x and y divided by the product of their respective standard deviations. And so we could kind of look at some plots of what rho looks like. So again, if rho were equal to 1, we would see the points falling directly on that straight line all together. If rho is equal to -1, we see something similar, except it's going in the opposite direction. And then when rho is equal to 0, we'll notice when rho is equal to 0, that also means that the covariance is equal to 0. So we see something like this. Right. Now, one thing to note here is the converse is not true. It is possible to have two random variables x and y such that the covariance is equal to 0, but x and y are dependent random variables. So this is really what we're talking about here in this note, is the idea with independence. So this really goes back with that previous comment up here, where if they're independent, the covariance is equal to 0, but this is saying that it is possible to have 0 covariance, but the random variables be dependent. Alright, so let's look at an example. Let's see how we could find the covariance and how we could find that correlation. Alright, so starting out here, we're going to find the covariance of x and y, and notice here I've went ahead and gave you what the expected value of x times y is, the expected value of x, and the expected value of y. So notice by our useful facts that we have up above, we know that the covariance of x and y is equal to the expected value of x times y minus the expected value of x times the expected value of y. So we can plug in these values that we have. This is equal to 59 divided by 144 minus 7 divided by 12 times 17 divided by 24, which is equal to -1 divided by 288. So notice this is very close to 0, but they are still dependent. And so if you go back and look at our previous notes, you'll see that we talked about this when we talked about the idea of independence in the previous note set. We could also find the correlation for this example. So note here that the correlation is equal to the covariance, which we just found, divided by the square root of the variance for x and the variance for y. So in order to solve this, we are going to need the variance for x and the variance for y. Now we've seen in previous note sets how to find that. So I'm just going to go ahead and give you these values, but I would encourage you as a good review to go ahead and make sure that you can find the variance for x and the variance for y. And you could do this one of two different ways. You could either use the joint distribution and look at the double integral, or you could find the marginal for x and the marginal for y and do it that way. But either way should yield these results. So then we can plug that in. And that gives us the following. And so again, this is going back to that idea that we just saw earlier, that if the covariance of two random variables is equal to 0, the variables need not be independent. Whereas the opposite is true. If they are independent, then we know that the covariance is equal to 0. All right, we've got some more useful expected value theorems. So let's look at some of these theorems. So we're going to start actually here with a definition. So we're going to define u to be a function of two random variables. It's going to be the sum of those two random variables where each of them are multiplied by a constant. Then what we can say is that u is a linear function of those two random variables. And so the next theorem is going to deal with linear functions of random variables. So if I have two sets of random variables, I'm going to have y1 through yn and x1 through xm. Those are all going to be random variables, and notice that the expected values for each of the yi's and the xi's are defined here. And then we're going to define two separate linear functions. We've got the linear function u1 and the linear function u2. So notice first that the expected value of u1 is going to be equal to the sum of those constants times the expected values of the x's. So in other words, if we look at that definition that we had earlier, we're actually saying this. We're saying that the expected value of u is going to be equal to a times the expected value of x plus b times the expected value of y. So that's what a there is saying. We get something similar for the variance, but notice for the variance that we have to square the constants and we need to account for the covariance. And then finally here we can look at the covariance between those two u's that are defined. And so here, if we're looking at the covariance, we get the following sum. So let's apply these to an example. Here we're going to suppose that y1, y2, and y3 are random variables. Notice here we have the expected value for all three of them. We have the variance for all three. And we also have the covariance for the three potential pairs between y1 and y2 and y3. And so we're going to define a u and a w, which are functions of those. And we're going to find some different expected values, variance, and covariance. So the first thing we're going to do is we're going to find the expected value of u. So first thing I'm going to do is plug in what u is equal to. And now I can apply that part A of the theorem that we have up above. And notice this is equal to the following. And then from here, we're given what these different expected values equal. So we have the following. And this gives us negative 62. We could also find the variance of u. So again, I'm interested in the variance of u. So the very first thing I'm going to do is I'm going to plug in what u is equal to. So now what I've got to do is for each of the terms that are in here, the first thing I'm going to do is look at their individual variances. So for the first one, I've got 2 times y1. So I need to square the 2 when I bring it out. So I'm going to have 2 squared times the variance of y1 plus 3 squared times the variance of y2. Now notice here my constant for y3 is negative 5, but when I square that, that is going to become positive. But just for completion, it's going to be negative 5 squared times the variance of y3. Now I'm not done here because I also need to account for the covariances. And so we're going to have the following terms. What the covariance is going to do is this term is actually going to look at all of the potential pairs. Now notice since we have 3 random variables, that means we have 3 potential pairs. So if you go back up and we look at our formula, Notice the first thing that we're going to have is there is a 2 in this formula, so I wrote down the 2. And now what we're going to multiply by is we're first going to look at our first potential pair, which is y1 and y2. So notice that y1 has a constant of 2 out front and y2 has a constant of 3. So we're going to have 2 times 3 times the covariance of y1 and y2. And then we're going to add to that, our next potential pair we could have is y1 and y3. Well, the constant in front of y1 is 2, in front of y3 is -5, and that's going to be multiplied by the covariance of y1 and y3. And then we have one final pair, which is y2 and y3. So similar, we're going to have 3 times -5 times the covariance of y2 and y3. So notice that the unknowns that we have here are those 3 variances and those 3 covariances. And if we go back up to the top, those are all given to us here. So we could plug those values in. I'm going to leave you to do that on your own and confirm that that does give you 51. And then finally, we could find the covariance of u and w, which are those 2 functions that are defined up above. So just to have it on this page, we've got that u is equal to 2y1 plus 3y2 minus 5y3, and w was equal to y1 plus 4y2. So in terms of our constants, notice here that a1 is equal to 2, a2 is equal to 3, a3 is equal to -5, b1 is equal to 1, and b2 is equal to 4. So we had the formula up above. So what I've done is I've rewritten that formula in terms of our example here. And so notice this gives us the following. And this is equal to 118. All right, we have another example here. Now, looking at this example, notice we've got y1 through yn are independent random variables where the expected value of all of the yi's is equal to the same value, and that is going to be mu, and all the variance of those random variables is equal to sigma squared. And what we're going to do is we're going to find the expected value of y bar and the variance of y bar, where y bar is equal to the mean, or we would say the sample mean. This is a very important result. And we're going to refer to this result later on in the course. So let's find that expected value of y bar and the variance of y bar. So first, again, note that y bar is equal to the sum of I equals 1 to n 1 over n yi. So the only thing I've done is pulled that 1 over n into the summation. So in other words, notice this is a linear combination of random variables. And in this case, what we have is that a1 is equal to a2 is all the way equal to an, and that's equal to 1 over n. So we can use part A of that theorem that we have up above, and we know that the expected value of y bar is equal to the expected value of the sum I equals 1 to n 1 over n yi. And since it's that linear combination, notice we can do the following. This is equal to the sum I equals 1 to n 1 over n times the expected value of yi. But we know that the expected value of all of the yi's is equal to mu. So that gives us the following, which is just equal to n times 1 over n mu, which is equal to mu. So the expected value of y bar, or the expected value of the sample mean, is equal to the population mean. And so you've probably seen this result before. It's a very important result because it gives us a rationale for using the sample mean to estimate the population mean. And again, we could do something very similar and look at the variance of y bar. So notice here, again, using the fact that this is a linear combination and part B of that theorem that we have up above, we get the following. But notice here that y1 through yn are independent. So since they're independent, we know that the covariance of yi and yj is equal to 0 by that independence. So this term actually goes away and we're just left with this piece. And we know that our a's in this case are all equal to 1 over n. And we know that our variance for all of the yi's was sigma squared. So notice we get the following. And this is also a well-known result. We know that the variance of y bar is equal to sigma squared over n. In other words, when we look at the standard error of y bar, think back to when you made confidence intervals for the mean. Back in your intro stat class, you have probably seen sigma squared over n. And this is exactly where that is coming from. So again, this is a very important result, and I'm going to reference this result later on in the course. So that ends this note set.